Okay, so we're going to be looking at the general properties of graphs and seeing if there's any patterns that occur in them. Basically, are there some patterns which are for definite regardless of what kind of graph you have, or regardless of like all simple graphs or stuff like that? And obviously, a lot of this would be based on other properties of the graphs or based on certain features of the graph. So we know the graph is made out of vertices and edges. So clearly, a lot of the patterns, if we find any patterns, would be connected to the vertices and edges of the graph, or the number of vertices and the number of edges of the graph. And perhaps there's a relationship between the two of them that's going to be set no matter what kind of a situation. And we kind of do know that there is a relationship between the number of vertices and the number of edges, because one, we've already looked at what the order of a graph is and what the size of the graph is, and we know that we can only have an edge if we have two end vertices kind of situation, or if it loops back on itself. So we do know that there's some sort of relationship between them. So now we're going to investigate those relationships to see if there's some general properties that we can make out just from these relationships. Okay, we're going to start off obviously with this connection between an edge is created with two end vertices, and we're going to narrow it down to simple graphs so that we don't have to consider this kind of a case, because, well, it's a little bit more challenging to look at. And we're going to try and investigate to see if we can come up with some sort of formula which will connect the two of them. So connect the fact that we have two end vertices with the fact that how many edges do we have in our graph kind of a situation. So we've already looked at this relationship when we spoke about the range of the size of the simple graph, and that gave us an inequality. So remember, it did give us that kind of inequality, which is n minus 1 divided by 2 kind of a situation. And inequalities are great. They give us some boundaries, but perhaps there is something out there that will give us equality. And inequality is like a very, well, you all know what equality is, but the whole idea behind it is it's a very definite relationship that will always work. So that's what we're going to investigate here. So let's just start off by drawing a bunch of simple graphs and just looking at some of their properties. So I'm just going to go to a new page for this. So we're going to start off with like the base case. So we want to investigate the relationship between the edges and the number of vertices and perhaps the degrees of the vertices. So we're going to need a graph that has at least one edge to begin with, kind of a thing. So let's say the most basic case, we have two vertices and one edge with a V1 and a V2. And let's investigate everything we know about it. So we say, okay, well, degree of V1 is equal to 1. The degree of V2 is equal to 1. We know that the order of the graph is equal to 2. The size of the graph is equal to 1. We also know that, when you look at the degrees of vertex E1 and the degrees of vertex E2, they both have E1 featuring in them. So they share, the count of the edge. They both count E1. Count E1. Okay, so let's go on to a slightly more complicated graph. And we're still going to keep it simple so that we can investigate and we can count and can do all this information. So let's just have 3 vertices. And let's have 2 edges there. Let's have that as E1 and that as E2. Okay, and what do we know from this graph? Well, we have the degree of V1 is equal to 2. We have the degree of V2 is equal to 1, and the degree of V3 is equal to 1. We have the order of the graph is equal to 3, and we have the size of the graph is equal to 2. Now, once again, we're like, well, in the one beforehand, we said, well, we counted E1 in the degree of V1, and we counted E1 in the degree of V2. Obviously, this is a very similar thing that is going to happen here. We saw it when it came to the range of the size, that when you go ahead and investigate that, your edges basically count twice there. And that's what we're kind of getting at here. We're looking for that pattern of just pointing out that, hey, the edges are going to count twice when you're looking at the degrees of the vertices. So I'm getting a little ahead of myself, but that's what we're aiming towards. So in the degree of E1, we have E1 counting and we have E2 counting. In the degree of E2, we have E1 counting, and in the degree of V3, we have E2 counting. So once again, we have the situation with this edge for E1 is counted twice in the degrees, and E2 is also counted twice. So hopefully at this moment in time, you're at least starting to see that if you had to add up the degrees of all the vertices, you would end up counting every edge twice. But in case you don't necessarily believe me, let's just do like one more example of this. So let's just take this exact same graph again, and let's make it an even simpler version. You can go ahead and investigate the slightly more complicated one. So I'm going to actually remove this edge here, just so that you can see what would happen in this case. Now you just have E1, and you have a look at your degree of V1 is equal to 1. The degree of V2 is equal to 1. The degree of V3 is equal to 0. Okay, we have the order of G is equal to 3, and then we have the size of G is equal to 1. And again, if we look at this, E1 is represented there, and E1 is represented there. So it is featuring twice if we look at all the degrees of the vertices. So it features when we're looking at all the degrees of the vertices twice. And that is the kind of pattern that we're looking for, and we look going towards. We look for a pattern, we see does the pattern exist, and then we are going to end up introducing you to the concepts of theorems where you'll prove that this pattern that you find is going to hold for all cases. But we'll discuss that in a bit. I just want to, show you the process, and then we can go to actually stating the theorem and then proving that the theorem is true. Okay, so we've noticed hopefully this pattern where if we had to add the degrees of all the vertices of the graph, it would count the edges twice. Now, if we had to write that in mathematical terms, which is a lot easier, we sum the degrees from I equals 1 to n, where your degree of vi, so it's the summation of the degree of vi, so that's basically for the first one, first graph here, G1, it would be, and I don't want to use the color yellow because it's really hard to see, so let's just do that, G1, that would be the degree of V1 plus the degree of V2, because our n would be 2. And if you go ahead and sum them, it would be the 1 plus the 1, and that would give us 2, right? But we know that E1 was counted here, and E1 was counted here. So we know that all the edges are counted twice. So we can say it's equal to 2 times m, where m is your number of edges, because if you think back to like previous work, we usually represented the number of edges with m. But the number of edges in a graph is also known as the size of the graph. So it's 2 times the size of the graph. So there is, a general property that will hold for all simple graphs, or we'll prove it will hold for all simple graphs in a bit. So that's the whole idea behind theorems and stuff. They're going to give us something that we can work with, aspects that will hold given a set of conditions. So let's just discuss the super basics of theorems. We'll introduce more and more information about theorems and proving theorems as we progress. Okay, so the bare basics of theorems. So the bare basics of theorems, the most super basic one is that you have some sort of condition or list of conditions. So it can be a bunch of conditions. And given those conditions, there will be some sort of outcome or result or property. Okay? And in notes or something, or textbooks and things like that, they usually refer to it as something like A implies B. And once again, I'm just going to be a bit pedantic about this. A is a list of conditions. And then given that all the conditions are met, so given that you have all of these conditions, it implies that B will, hold or exist. Hold, exist, whatever, it depends on the actual theorem that you're doing. So, for example, in graph theory, you would have maybe say that it is a simple graph as a condition, and from there you'll be like, okay, it's a simple graph, it has maybe, a specific order and a specific size. Then given those conditions, we will have that the sum of the degrees vi is equal to 2m, where I is 1 to n. So given that it is a simple graph, and a simple graph means, no loops, no parallel edges, undirected, all that kind of stuff. It's just, the super basic kind of a graph with no loops and parallel edges. And if the order is n, and you'll see n pops up in this, the outcome that we're looking at, and the size is m, the m, pops up kind of there, this whole thing will be true. So that's, the most bare basics of theorems. They do get slightly more complicated. We'll go through the process, as we introduce them. But for now, the whole idea is we have a list of conditions. If we meet those conditions with whatever we're looking at, then the B part will hold. And then we also need to, so you will obviously get a lot of theorem statements, and you will learn those theorem statements because they're really useful in solving puzzles and stuff, because you have this outcome that's always going to hold. You can use it to prove other things, kind of a situation. But another aspect behind theorems is proving it. So we'll also have to look at ways to prove that, given this list of conditions here, we will get this outcome over here. And the first way that we're going to look at is just referred to as a direct proof. In other words, we're just going to take all these conditions here, and we're just going to try and form a logical sequence to show that no matter the case, as long as it holds for everything that we have stated for the conditions, it will always have B pop up. Now, one of the most important things is when you're doing the proof situation of this, is just remember you can't just give one example. So you can't just tell me, hey, a graph of order 3 and size 2 gives me, the sum of the degrees equal to 2 times the size. You have to show for all n's, which means n is, finite, but you have to be able to show that no matter how many vertices the graph has, whenever you sum up the degrees of the vertices, it's going to be equal to 2 times the size of the graph. So you can't just use one specific example. The specific example situations can be utilized to form a counterexample, in other words, to show that the theorem statement that someone has given you is not true and therefore not a valid theorem. But if you're proving that a theorem is true, it has to hold for all cases. So you can't just look at one example, you have to look at all cases. And that's something just to like hammer into your head right now, because it's going to be a mistake you will make later on. Or you'll do it quickly for one example and be like, sure, it works, and just move on. But you have to show it works for all, not just for one version of it. Okay, so now we have the theorem statement. We have, the graph, and it's the graph G with the pair of, the set of the vertices and the set of the edges, and we can refer to it as the set of the edges because it's a simple graph. Therefore, there are no multiple edges, so it's not a multiset. And we basically state in here by this, we stating that the order is the n, and by this over here, we stating that the size is m, from this little n there and the m over there. And then again, we have the sum of the degrees of vi is equal to 2 times m, which is also 2 times the size of the graph. Okay, so you can see theorem statements written slightly differently, but representing the same, thing. So that is something to just consider and be aware of as well. Now we're going to try and prove it. And the reason why I approach, the explanation to bring into theorems and proofs and everything, the way I did was I kind of already started showing you how you could start thinking about proving this by investigating, the basic case and then extending it and seeing if there's any sort of, pattern. So the very same way that you'd build up a theorem statement is going to be utilized to help guide you in your proof. Obviously, you're going to want your proof to be neater and prettier and more elegant. The elegant will be used a lot in mathematics for this. But basically, a more taking away the messiness of figuring out that theorem statement and showing it works. You're going to want to like neaten it up, kind of like when you write a first draft of an essay and then you go through and you take out the unnecessary words and all that kind of situation. So that's the kind of approach. Often you will be given the theorem statement. We will not expect you to just build up theorem statements by yourself. I mean, you are just in first year. Like, let's keep the expectations at the correct level. But the whole idea is you would use a very similar process in learning how to prove. And a lot of the proofs that we're going to be doing in this course will give you some sort of, techniques and tricks to just add it to your toolbox when you reach other proofs or other problem solving skills. So a lot of the times, yes, these theorems that we cover and the proofs that we cover are very important, but they're often very important because the underlying techniques in them teach you how to think about the mathematics and approach the mathematics in a different way. So it's not just, you need to know this theory. It's because knowing this theory will help build up your toolkit for solving problems later. So let's go through how we can do this proof. So we kind of already looked at how we could do this proof by investigating those other, mini graphs. And we saw with the basic graphs that there was a situation where whenever you looked at the degrees of the vertices, when you look at the degrees of the vertices of all the graphs, the edges count twice. So we know from our exploration earlier that the edges are counted in the degree of the vertices twice. Why? Because it'll be, you have your two end vertices. And now we need to basically write it in a slightly more general way, this idea or this, concept for our proof. Okay, so for the proof, we have to remember we have to show for the most general case. So for this one, we know that we want to talk about the fact that every edge is counted twice in the degrees of the vertices. So we need to discuss a general edge, an edge that, could represent any of the edges in the graph. So we're going to actually say that. We're going to say, let E be any edge in G. And let's give the end vertices of this edge, which can represent any edge in G, names as well, just to help us out. And E is equal to, let's have VK and VT. Okay? I know that looks like an R, but that is a VK. So again, we're just giving any arbitrary like placeholder names kind of a situation, and that's just to help us out in explaining to the reader or user, what exactly is going on. So again, for a proof, we're going to want to show for the general case, in other words, not a specific example, but for like any graph that fits these properties. So in this case, we say, okay, let's work with any edge in G. Let's just give it two end vertices some symbols so that we can work with it from there. And then we say, okay, let's look at the degrees of the vertices connected to this E, or the specific edge that we're talking about, which can be any edge in G. So if we look at the degree of VK, We know that when you're looking at the degree of VK, because it's a simple graph, the degree of VK counts every edge once. Okay, the degree of VK counts every edge once. And this includes, that arbitrary E, because, E is made out of VK and VT. Then let's look at the degree of VT. If we look at the degree of VT, the degree of VT also counts every edge once that's connected to it. And the degree of VT counts E as well. Okay, so we don't really care about the fact that, it counts every edge once. What we're more caring about is the fact that it's going to count E as well. Because remember, the whole idea here is we're trying to prove that 2 times, the number of edges situation. So again, we just had any edge in G, we gave it a name, we gave it some arbitrary placeholder, n vertices. Then we looked at the degree of one of the n vertices, and we said, well, we know when we look at the degree of the vertices of a simple graph, it's going to count every edge once that's connected to it. And in this case, the way that we set it up with the E, it's going to include E in that count. Then we look at the second n vertices. So we're looking at the degree of ET, and we say, hey, the degree of ET also counts E. Okay? And if that's the case, therefore, we have the situation that the sum of the degrees of the graph counts every edge twice. And therefore, the sum of the degrees of the graph is equal to 2 times m, or equal to 2 times the size of G, depending on which version of the theorem statement you are solving. And then we've done it. We have proved it pretty much directly. We, took some properties of all the conditions of the graph. So we knew that it was, that simple graph, and that's where we have the counts every edge once situation, because again, you don't have any loops occurring or anything like that. We knew that the graph had an order n, and we utilized that in our, descriptions here. We also knew that the graph had a size m. We utilized that as well. So we used all the conditions given to us of that theorem statement, and in this case we kind of just proved it directly. So we just went at it and said, given all this information, this is going to be the outcome, and it's always going to be the outcome, and that is referred to as like direct proof. So we just went through the math and showed that it will be true. Now, things to note, a lot of people will finish off their proofs with a little square at the bottom kind of a thing, just be like the proof is finished, or they'll use QED. And again, that is just to like say, hey, my proof is finished. So if you're reading notes or anything like that, you will see one of these, represented, in the notes or in the textbooks and stuff like that. So that was your first introduction to a theorem, in this module. It was a direct theorem. It had, a list of conditions, which were part A, and it implied part B. And one of the things I just want you to try to get the hang of is identifying what fits the A part of the theorem, in other words, the conditions, and what is the outcome of it. So what is part B? And that's going to help you in pure math. It's going to help you in applied math. It's probably going to help you in some other modules as well, just for, your problem solving skills. So you can start, piecing things together just slightly better and start learning how to approach, like, okay, given this, can I get this kind of situation? Okay, so next up on our journey of theorems is a situation where we will have some proposition or theorem statement, which is actually proved utilizing the previous theorem statement. So it's kind of like a subsection in a way. So this is the corollary, And the whole idea behind this is it can be proved from the previous proposition, which means you are going to need to know what the previous proposition is and have some familiarity with it in order to understand where, this next theorem statement, which just has a fancy name, comes from. And again, the fancy name is just there to show that, when you prove it, the proving of it comes from the previous one. So what do we know about the previous one? We know that the sum of the degrees of the vertices is equal to 2 times the size of the graph, or 2 times m. So whatever we, getting from here, this piece here comes from, or is going to be proven utilizing that, the B part of the previous theorem. So in this one, it says that every graph has an even number of vertices of odd degree. So to go about proving it, again, we're going to utilize the previous one. And again, we're not going to do anything fancy yet. We are just going to stick with a direct proof. So the first thing we're going to do is we're going to need to look at, okay, what do we have? Well, we have, a situation where they say every graph has an even number of vertices of odd degree. That means that the fact that they say odd degree means that they are separating the degrees of the vertices into those that have odd degree and those that have even degree. So when it comes to our proof, we're obviously going to want to at least separate those two out. So we are going to want to discuss the degrees of the vertices which equal to an odd number, and the degrees of the vertices which equal to an even number. And we're going to want them, like separate sets. Then we talk about an even number of vertices of odd degree. So we need to somehow figure out or show that if we sum up all the odd degrees, we are going to get an even number out of it. Now, technically, we already know that should work out, because if you go ahead and sum, 2 odd numbers, for example, you will get an even number. So this is, again, it's in the realm of mathematics you should be kind of familiar with. You can, by the way, you can pause it right now and actually just go ahead and look at it and add up 2 odd numbers, then add up 4 odd numbers, and add up 6 odd numbers, just to show that it's always going to bring out an even number. And then you can come back. And if you come back, you'd be like, okay, so sure, if we have, vertices of odd degree, so they're odd numbers, how do we show that there will be an even number of them? Like, why will there be an even number of them? And you'll be like, okay, I can show there's an even number of them if the summation of the degrees of the odd degree vertices is equal to an even number, because I know that the summation of an even number of odd numbers is going to give me an even number. That's what you just did with the pausing. So let's actually just write that down. The sum of an even number of odd numbers equals an even number. Okay, so that's what you went and investigated during the pause, where you just went and added up a bunch of, odd numbers, an even amount of them, so 2 of them or 4 of them or 6 of them, and you kept seeing that it showed an even number. So we're going to utilize that. But then you had that moment, and I'm repeating myself now, of, okay, even if I do know that an even number of odd numbers gives me an even number, how is that going to help me show that there is an even number of vertices of odd degree? And the idea behind that is, if you can show that the sum of the odd degree vertices is equal to an even number, it implies that the number of odd degree vertices is even, because of, this statement. So a very long roundabout situation in explaining what's going on. So let me discuss this one more time. Let's take that away. And let's take that away. Let's take all of this away. So one more time, we have the situation where we have the corollary and it is based on the previous theorem. So the previous theorem, we had the sum of the degrees equal 2 times the size. And then this one says every graph has an even number of vertices of odd degree. So an even number vertices of odd degree. We think about what do we know about odd numbers, because if we're looking about odd degrees, they are odd numbers. And we know that this is the sum of the degrees. So when we're looking at that, we're technically going to be summing up odd numbers. So we know that an odd number plus an odd number is equal to an even number. We also know that 3 odd numbers is an odd number, but that's not important to us right now. So we eventually reach the point where we're like, well, as long as you have an even number of odd numbers, when you sum them up, it's going to give you an even number. And then you're like, wait a second, you sum up an even number of odd numbers gives you an even number. So we have a summation here, and we could try and get it so that the summation is just, the vertices of odd degree, so there will be odd numbers. If we can show it's even, then we know there's an even number of those vertices of odd degree. So let's go about trying to do that. So to try and do that, we also need to then consider the fact that this whole thing is the summation of all the degrees of the vertices of the graph. So is there a way that we can split up the vertices of the graph into, subsets where we have one subset is all the odd degree vertices and one subset is all the even degree vertices. So we break it up into subsets of odd degree vertices. And I'm talking about this, I'm talking about the degree of vertices. I'm not saying, you've labeled your vertices odd numbers. I'm talking about the degrees of the vertices and even degree vertices. And what's really nice is we know from previous work, when you have a graph and you have a graph, say, something like this, and let's call it V1, V2, V3, V4, and V5. We can relabel it. So we can always, let's first investigate it and be like, so the degree of V1 is 1, the degree of V2 is 3, the degree of V3 is 1, the degree of V4 is 2, and then the degree of V5 is 1. But we can relabel it so that all the odd degree vertices are numbered first. So we could rename this as still V1, but we can still keep, okay, we still keep V2, we still keep V3, but we don't use V4 because we want all the odd degree vertices labeled first. So we rename, this one V4, and then we make this one V5. Then when we discuss it, we basically have, from I equals 1 to 4, the degree of VI are all the odd degree vertices. So we can, relabel our graph and restructure the way that we label our graph to clump together all the odd degree vertices. And then we'll have plus the degree of V5 in this case, which is all the even degree vertices. And then we have it 2 times the size of the graph. And obviously this whole piece here is the original I equals 1 to 5, the degree of VI. So that's what we're going to do. So we're going to be like, let's rename or restructure our graph. Also, we're looking at the general case, so we actually don't even have to say restructure. We can just say, listen, all the odd degree vertices go from V1, say, to VK, and then all the even degree vertices go from VK plus 1 all the way to the order of the graph, the Vn. And then we can, utilize what we've just done here And the reason why we want to do this, and I don't want to write down the proof yet, is because we know that the sum of even numbers is even, right? So if you had a bunch of these, leftover even degree vertices and you shove them to the other side, you know it's an even number. You know 2 times any number is even. So an even number minus even number is an even number. And then you've already shown that the summation of the odd degree vertices is equal to an even number, which is the whole point of the situation. So again, it's the whole idea is we go, there's a couple things that we do here. So even though it looks straightforward, it's quite a lot of layering, where we looked at the corollary and we said, okay, it says every graph has an even number of vertices of odd degree. What do we know about even and odd numbers and the adding of even and odd numbers? Well, we know that an even number of odd numbers always gives us an even number. We know that if we sum in our odd degree vertices, then if we can show that the summation of the odd degree vertices is equal to an even number, then we have shown that there is an even number of odd degree vertices. You may want to slow that down and re-listen to it, because I understand it is a lot of even and odd wordage that is being used, terminology, language. So how do we show the summation of the odd degree of vertices is equal to an even number? Well, we say, okay, well, we have the simple graph. Can we generalize it in such a way that we have a subset for all the odd degree vertices and a subset for all the even degree vertices? And we relabel it so that we can, it just works out prettily when we do the math. That's what we did here, where we said all the odd degree vertices get labeled first and all the even degree vertices get labeled afterwards. So all the odd degree vertices got labeled first. That is our, up to, in this case, 4, but we can have an arbitrary placeholder there of, like, say, k, and then anything after that is an even degree vertice. And that's where we, get that kind of situation occurring. Then we can go in and we say, well, we know the summation of a bunch of even numbers is an even number. We can shove it over to the other side and we have an even number minus even number. That gives us an even number, and then we sort it. We have proven the general case. So let's actually go ahead and do that now. Okay, so to prove it, we need first to break up those subsets of the vertices into even and odd degree. So let's say if vertices V1, V2, all the way to Vk have odd degree. So again, we're just breaking up our graph into the odd degree vertices and the even degree vertices and relabeling it such that we can do it like this, with that nice numerical order. Then vertices Vk plus 1 to Vn have even degree. And this will hold for, any graph that we're doing, any simple graph that we're doing. The reason being, it could hold for the previous one. Our k would then be equal to 4, and it can hold for a case where we only have one, well, we can't have one vertice of odd degree, but it will hold for the case where we have the situation of, say, k is equal to 2, and so on. So it's going to fit, it's the general case, because remember, when you're doing a proof, you need to prove the general case, not just one example. By all means, when I explain it to you, I explain it to you using one example, just so you can get a visualization where possible. But when you actually prove it, we need to prove for all cases, and laying it out like this allows us to prove for all cases. Then from Theorem 1, and I'm referring to it as the Theorem 1 in the notes, just be aware of that. But generally, you do not want to utilize numbers for your theorems unless you've stated it and it's in a report, mainly because the theorem's numbers can change depending on what text you're using, what notes you're using, how you're writing it yourself, and so on. So then from the summation I equals 1 to n, the degree of vi is equal to 2 times m. We then have the degree of v1 plus all the way to the degree of vk. So those are your odd degree vertices. And then you have plus your degree of vk plus 1 all the way to, your degree of vk. And again, these are just going to be the general situation for all your even degree vertices. You can also write this as, I equals 1 to k of the degree of vi plus the summation I equals k plus 1 to n of the degree of vi. And we know that this is equal to 2 times m. That is equal to 2 times m. Now we're going to take this summation of the even degrees and just take it across. Okay, so we're left with the summation of all the odd degree vertices is equal to 2m minus the summation of all the even degree vertices. But we know that, again, that's even, and that will be an even number because the sum of even numbers will always be even, and the degrees of literally the vertices v1 to vn have even degrees, so all of those are even numbers just added together. So we have is even, and therefore, from the fact that we know that if you summing up a bunch of odd numbers and you get an even number out of it, it must be an even number of odd numbers. And therefore we have that k is even, and we are done with the proof. Okay, so again, there's a lot of word use of even and odd repeated through the process. I did over explain it, but the idea was, just get you thinking about like, what math do you know? Can you connect the math? What are your outcomes? And going from there. Don't forget to again go through your theorem statements, figure out what are your conditions and what is the outcome so that you can utilize it in your direct proofs. Because remember, as usual, we use all the conditions to prove the outcome, which is that k is even. So there's an even number of odd degree vertices. So what were the conditions? It was a simple graph, and a simple graph, with order n, size m. And what do we know about simple graphs? So the fact that it's a simple graph means we had all the information that from previously that we've known about simple graphs to use in trying to prove our outcome, which is that the sum of the odd degree vertices, well, the number of odd degree vertices is even. So the thing that we knew about simple graphs directly from a theorem we just covered was the sum of the degrees. So you can see where you have your conditions, then you look for, is there anything in those conditions where you have extra information that you can utilize? And then can you, utilize that information then to get down to your outcome? So knowing what your conditions of your theorem statement is and what the outcome is helps you piece to piece the beginning part and the end part of your proof. And then the middle part is like, well, what math do I know? And can I connect the math up to get me to, the end part, at least for a direct proof approach?